Hello. The quietest yet most powerful force in the universe. Gravity. We cannot see it or touch it, yet its presence makes itself felt in every moment of our lives. In the path of a stone falling from our hand, in the tides the moon raises in the oceans, even in the cosmic dances of planets in their orbits. Behind all of these lies an unseen bond: gravity. Throughout history, humanity has tried to understand this mysterious force through a journey that runs from philosophers to scientists, from myths to modern physics. Now, let us explore together the universal dance of this invisible force. The invisible force. Definition and importance of gravity. Gravity, or, in physical terms, gravitation, is one of the most fundamental and most mysterious forces in the universe. It cannot be seen or directly felt, yet its effect is everywhere. It is the main actor of an invisible dance that allows us to stand on the ground, that keeps planets in their orbits, and that holds stars and galaxies together. The gravitational force is based on the principle that all matter in the universe attracts all other matter. This attraction depends on the masses of the objects and the distance between them. For example, the mass of the Earth is so large that it pulls every object on it, from a pencil to colossal buildings, toward its own center. This pull is the underlying reason for what we perceive as falling to the ground. But gravity is not limited to Earth alone. Grand-scale phenomena such as the moon causing tides on Earth, the sun holding the planets in orbit, and stars collapsing to form black holes are all products of gravitation. In fact, even light cannot escape from a sufficiently strong gravitational field, as demonstrated by Einstein's theory of relativity. Gravity is a weak force. Compared with electromagnetism or the nuclear forces, it is far less intense. However, on the largest scales and for the most massive objects, it is the only decisive force. For this reason, gravity is a cornerstone for many fields of science, from cosmology and astrophysics to engineering and even biology. To understand gravitation is not only to understand physics, but also to understand how the universe works, why it is so ordered, and how it is possible that we exist on this planet at all. For this invisible force is almost like the cement of the cosmos. It prevents everything from flying apart, preserves structure, and steers matter and time as a kind of cosmic power. Ancient perceptions, from Aristotle to Avicenna and the place of mass. Although the concept of gravity appears to be a product of modern physics, its roots stretch back to ancient philosophy. While trying to explain the order of the cosmos, ancient Greek thinkers also questioned natural motion and weight. These inquiries formed the first steps of scientific thought. Aristotle believed that every object in the universe had a natural place. According to him, matter was composed of 4 elements: earth, water, air, and fire. And each element moved according to its nature either upward or downward. earth and water tended downward, while air and fire rose upward. This understanding did not truly explain gravity, but instead attributed observable falling to the nature of the elements. Heavy objects fell to the ground because their earthly nature belonged to the earth. This view dominated Western thought for centuries, yet Aristotle's explanation was not quantitative. Concepts like force, speed, and time were not defined in ways that could be scientifically measured. Questions such as why objects accelerate as they fall, or why different objects do not necessarily hit the ground at different times, remained unanswered. In the Middle Ages, especially in the Islamic world, scientific thought took on a different character. Avicenna, Ibn Sīnā, although largely accepting Aristotle's ideas, developed more systematic interpretations of the nature of motion. According to Avicenna, if an object was moving, there had to be a cause sustaining this motion, an internal inclination, or male. This male was an inner factor that preserved motion. This idea later evolved in the West into the impetus theory and helped pave the way for Newtonian physics. Scientists such as Ibn al-Haytham and al-Biruni also contributed experimentally and theoretically to concepts like falling motion, speed, and force. Their observation-based approaches strengthened the belief in the mathematical nature of the universe. In ancient and Islamic thought, gravity was not expressed in the modern sense, but notions of weight, falling, and motion evolved during these periods. The accumulated knowledge would gradually transform, and, with the Renaissance, become the groundwork upon which Galileo and Newton would build the modern theory of gravitation. Galileo and falling bodies, a paradigm shift. By the end of the 16th century, a profound transformation in humanity's understanding of nature had begun. One of the leading figures of this transformation was the Florentine scientist Galileo Galilei. Galileo was not only an astronomer, but a thinker who reshaped natural philosophy with his insistence on observation, measurement, and experimentation. His studies on falling bodies stand as one of the clearest examples of this scientific revolution. The Pisa Tower experiment, myth or reality? The famous story claims that Galileo dropped spheres of different masses from the Leaning Tower of Pisa and observed that they struck the ground at the same time, directly contradicting Aristotle's long-held belief that heavier objects fall faster. Whether this experiment truly happened is still debated, but its symbolic meaning is undeniable. It represents Galileo's challenge to centuries-old assumptions and his determination to replace inherited belief with measurable evidence. The experimental revolution, the rise of observation and measurement. Before Galileo, the behavior of falling objects was explained mainly through philosophical reasoning. Galileo was the first to transform this into an experimental field. Using inclined planes and carefully timed observations, he discovered that falling objects do not move at a constant speed. Instead, their speed increases steadily as they fall. In other words, their motion is accelerated. This realization marked the first quantitative step toward understanding how motion works in the natural world, not through speculation, but through measurable patterns. Birth of the laws of motion. These insights formed the foundation upon which Isaac Newton would later build the laws of motion. Galileo showed that objects do not move simply because it is their nature to do so, but because forces act on them. He also recognized that an object in motion tends to keep moving unless something acts to stop it, a concept that became the essence of Newton's law of inertia. Galileo, therefore, did not merely observe falling bodies. He set the stage for the entire mathematical framework of classical mechanics, a paradigm shift. Galileo's work represents a turning point not only for physics, but for the entire history of scientific thought. By uniting observation, experimentation, and mathematical reasoning, he laid the groundwork for a new worldview in which nature could be understood through universal principles rather than ancient authority. His study of falling bodies, simple as it seems, became one of the seeds of the modern scientific revolution. Newton's apple. The universal law of gravitation. One of the greatest milestones of the 17th century scientific revolution was the universal law of gravitation, formulated by Isaac Newton. The ideas first shaped by Galileo through experimentation were elevated by Newton into a unified, comprehensive framework, becoming the first physical theory capable of describing both earthly motion and the motion of celestial bodies. The legendary apple story. The famous tale of Newton sitting under an apple tree and contemplating gravity as an apple fell is more symbolic than literal. Whether it truly happened does not matter. What matters is the insight it represents. Newton realized that the same force pulling the apple downward could also govern the motion of the moon and the planets. This was a revolutionary idea that the heavens and the earth follow the same physical rules. Newton's universal insight. In his monumental work, Philosophiae Naturalis Principia Mathematica, Newton proposed that all objects in the universe attract one another. This attraction becomes stronger for larger masses and weaker with increasing distance. With this simple but profound principle, Newton unified countless natural phenomena under a single framework. The fall of objects on Earth, the moon's orbit around the Earth, the planets' paths around the sun, the rise and fall of tides, even the trajectories of comets. For the first time, a single idea explained both everyday experiences and the grand motions of the cosmos. Newton's revolution. The universality of natural laws. Newton's achievement was not merely the discovery of a law, but the realization that nature is consistent everywhere. Gravity was no longer a force limited to Earth. It was a universal interaction shaping stars, galaxies, and the vast structure of the universe itself. This view supported the rise of the mechanical universe, a cosmos governed by predictable, orderly laws. From geometry to dynamics, Newton's genius also lay in turning motion into a cause and effect relationship. He showed that orbits, accelerations, and changing velocities were all consequences of gravitational interaction. The elliptical paths discovered earlier by Kepler suddenly had a clear explanation. Astronomy transformed from observational study into a deeply mathematical science. The center of scientific thought, Newtonianism. For nearly 2 centuries, Newton's gravitational theory became the backbone of scientific understanding. It influenced not only astronomy and physics, but also engineering, philosophy, and the technological leaps of the Industrial Revolution. Newton came to symbolize the belief that the universe could be described, predicted, and understood through reason and calculation. Einstein's curved space, relativity, and the nature of gravity. At the beginning of the 20th century, Newton's law of gravitation was still valid in many domains. However, when extremely large masses and very high speeds were involved, the law began to fail. In 1915, Albert Einstein changed the course of physics with his general theory of relativity. This theory not only redefined gravity, but also transformed the very nature of space and time. A geometric theory, instead of Newton's force. According to Einstein, gravity is not a force acting between objects. Rather, it emerges from the way massive objects curve the fabric of space-time. A massive body bends the space-time around it, and other objects move along this curved geometry. This can be visualized like a bowling ball placed on a stretched sheet. It creates a depression, and smaller objects rolling nearby follow curved paths because of this distortion. Planets and moons similarly move along the curved space-time shaped by stars and planets, and appear as if they are being pulled. What is space-time? In Einstein's view, space and time are not separate, fixed backgrounds. They form a single, 4-dimensional fabric called space-time, which can be bent, stretched, and warped. In this sense, gravity is a geometrical phenomenon. As mass curves, space-time, motion, and the flow of time in that region change accordingly. Bending time. Gravitational time. Dilation. Einstein's theory affects not only space, but also time. Near large masses, time flows more slowly. This effect is a real phenomenon and must be taken into account, for example, in GPS satellites. The clocks on board satellites run faster than clocks on Earth's surface, so corrections based on general relativity are necessary. This gravitational time dilation is one of the most spectacular consequences of relativity. Bending light, a visible proof. One of Einstein's predictions was that light is also deflected by gravitational fields. In 1919, during a solar eclipse, British astronomer Arthur Eddington recorded that the apparent positions of stars shifted as their light passed near the edge of the sun. This observation demonstrated experimentally that even light is affected by space-time curvature, and brought Einstein worldwide fame almost overnight. Black holes, from theory to reality. Solutions to Einstein's field equations gave rise to the concept of black holes. Karl Schwarzschild, working with these equations, showed that if a mass were compressed beyond a certain density, It would warp spacetime to such an extent that not even light could escape from a particular region, the event horizon. Einstein was initially skeptical about such objects, but his own equations made black holes a mathematical necessity. Einstein's legacy, a universal geometry. General relativity is used to explain not only the motion of planets, but also the expansion of the universe, the structure of galaxies, and even the cosmic microwave background radiation. It is the cornerstone of modern cosmology. Today, black holes, gravitational lensing, gravitational waves, and even ideas about time travel are studied within the framework of this theory. Gravity on Earth, from pendulums to blood pressure. Gravity is not only a cosmic force that keeps planets in orbit, it is also the invisible helper that shapes every moment of our daily lives on Earth. In this section, we will explore effects of gravity ranging from scientific experiments to its role in engineering. Gravity in everyday life. At the most basic level, the fact that our feet remain on the ground when we walk, that objects in our hands fall to the floor, or that liquids flow into containers are all due to gravity. Gravity regulates blood circulation in our bodies, holds the atmosphere to the Earth, and makes life, as we know it, possible. Simple machines and timekeeping. In the 17th century, pendulum clocks made it possible to use gravitational force in time measurement. Galileo's observations about the isochronous swing of pendulums paved the way for modern clockmaking. Pendulums also became fundamental tools for measuring Earth's gravitational acceleration. Use in experiments. Gravitational force has become a basic parameter in scientific experiments. For instance, free-fall experiments show that bodies move independently of their mass under gravity. These experiments provided the experimental basis for Newton's laws and later for Einstein's general relativity. Engineering and space technology. In engineering applications, gravitational calculations are indispensable. Building design, bridge construction, aircraft trajectories, and satellite orbit calculations all depend on gravity. In particular, during space travel, calculations of escape velocity for rockets rely directly on gravitational formulas. Role in modern technology. Many of today's sensitive instruments take gravity into account. Gravimeters are used in mineral exploration and in mapping underground structures. Precision balance devices are calibrated to be unaffected by local gravitational variations. Different gravity in different places. The Earth's surface is not a perfect sphere, so gravitational strength differs slightly at the poles and at the equator. These differences must be taken into account in satellite navigation systems, marine navigation, and even in performance analyses of certain sports. Orbits and balance. The dance of the planets. One of the most elegant manifestations of gravity is the quiet and harmonious dance of planets and moons in space. This cosmic choreography is not only a visual spectacle, but also a mathematical reflection of the laws of gravitation. From planets orbiting the Sun to artificial satellites circling the Earth, every motion is shaped by the delicate balance of an invisible force. Johannes Kepler was the first to express this balance in a meaningful way. Using the observational data of Tycho Brahe in the 17th century, Kepler discovered that planets follow elliptical orbits around the Sun. Kepler's three laws became cornerstones of not only the history of astronomy, but also of modern physical thought. Especially the second law, the area law, which states that planets move faster when they are closer to the Sun and slower when they are farther away, opened an intuitive window onto how gravity's influence changes. Isaac Newton later provided the mathematical proof of Kepler's insights. With his universal law of gravitation, he revealed the force behind the Keplerian orbits, showing that planetary motion rests not merely on observation, but on universal physical laws. The practical application of these principles appears in modern space technology. Artificial satellites revolve in stable orbits around the Earth, carrying out critical tasks such as communication, weather forecasting, GPS, and scientific research. A satellite stays in orbit thanks to a delicate balance between two effects, gravity and centripetal motion. Gravity constantly pulls it toward the Earth, while its orbital speed prevents it from falling, allowing it to fall around the Earth instead of onto it. This situation can be likened to a stone whirled on a string. Kepler's orbital mechanics applies not only to natural bodies, but also to man-made ones like spacecraft and space stations. The International Space Station, ISS for example, orbits the Earth at about 400 km altitude at roughly 28,000 km, completing one orbit in about 90 minutes. Objects that move more slowly than required fall back to Earth, while those that move too fast escape into space. Thus, orbital motion is not just a chosen trajectory, but a physical necessity. This topic allows us to explore not only where celestial bodies go, but also why they move in those particular ways. It is also directly linked to modern issues such as satellite collisions, orbital debris, and Lagrange points, key concerns in contemporary space engineering. In short, the orbital motion of planets, satellites, and spacecraft is a graceful example of Newtonian mechanics and gravitation. Each revolution is a cosmic waltz in which gravity and inertia, speed and attraction, chaos and order are maintained in delicate balance. And this waltz composes the most magnificent choreography in the universe. Gravity does not only shape the orbits of planets, it affects every layer of biological systems, from the structure of cell membranes to bone density. Life has evolved in continuous interaction with this invisible force. On Earth, living organisms do not experience gravity merely as a pressure they feel, but as a physiological necessity. At the cellular level, gravity plays a decisive role in the distribution of fluids and the balance of internal pressures. Without gravity, the positions of cellular organelles, the functioning of ion channels, and even the mechanics of cell division might change dramatically. This could influence processes ranging from embryonic development to immune system responses. Bone tissue is one of the structures most intensely connected with gravity. Gravity constantly stimulates bone cells, helping them maintain mineral density. In space, that is, in microgravity conditions, this stimulus disappears. Osteoblast activity, bone-forming cells, decreases, while osteoclast activity, bone-resorbing cells, increases. This leads to rapid bone loss. A similar process occurs in muscle tissue. Muscles that work against gravity, such as those in the legs and back, quickly weaken in microgravity. For this reason, NASA enforces strict exercise regimes for astronauts on space missions. The cardiovascular system is also heavily affected by changes in gravitational influence. On Earth, the heart must pump blood upward against gravity. In microgravity, this resistance disappears, and the heart muscle gradually weakens. Moreover, the redistribution of bodily fluids causes swelling in the face and a decrease of fluid in the legs. This disrupts the homeostatic mechanisms that regulate fluid balance. The vestibular system, which governs our sense of balance and is located in the inner ear, is also sensitive to gravity. It detects the position and motions of the head and sends balance information to the brain. In microgravity, these signals become confused. Astronauts often experience dizziness and disorientation in space. This provides important data on how long-term life in space affects the nervous system. These effects are not limited to outer space. Under Earth conditions where gravity's effect is increased or reduced, similar behaviors can be observed. For example, patients who remain bedridden for long periods suffer bone and muscle loss very similar to that seen in space. Thus, gravity is critically important not only for space medicine, but also for understanding clinical conditions such as aging, osteoporosis, and prolonged immobility. In conclusion, gravity does more than press us to the ground. It is a fundamental biological parameter that helps coordinate our bodily systems. Its absence or alteration compels living organisms not only to change their movements, but to reorganize their cellular functions and organ systems from the ground up. Gravity acts like an invisible guide, shaping the very form of life. The extreme faces of gravity: black holes, waves, and anomalies. Although gravity is a familiar force in daily life, it behaves in unconventional ways under the universe's most extreme conditions. These extreme faces have pushed classical physics to its limits and paved the way for modern physics. Black holes, gravitational waves, and the dark components of the universe, dark matter and dark energy, go beyond the familiar nature of gravity. Black holes, points of infinite curvature. Black holes, which follow directly from Einstein's general relativity, are regions of spacetime where mass has warped the fabric so intensely that not even light can escape. Formed when massive stars collapse at the end of their lifetimes. Black holes represent the most extreme manifestation of gravity. The boundary from which neither matter nor information can return is called the event horizon. Black holes are not merely astronomical objects, they are also cosmic laboratories that test the consistency of the laws of nature. Gravitational waves, vibrations of space-time. When Einstein proposed in 1916 that space-time could ripple like a fabric, this remained a theoretical prediction for a long time. But in 2015, the LIGO Observatory directly detected gravitational waves produced by the collision of two black holes. These waves are like echoes of the universe, massive collisions, mergers or supernova explosions send ripples through space-time. Today, gravitational waves have created an entirely new branch of astronomy that reveals invisible cosmic events, cosmic anomalies, dark matter, and dark energy. On cosmic scales, galaxies and stars account for only a small portion of the universe's total content. Measurements suggest that about 27% of the universe is dark matter and about 68% is dark energy. Dark matter is invisible because it does not interact with light. Its existence is inferred only from its gravitational effects. It provides the unseen skeleton that explains the rotation speeds of galaxies and the cohesion of cosmic structures. Dark energy, on the other hand, is a mysterious influence believed to drive the accelerated expansion of the universe. Here, gravity seems to play an unusual role, not as an attractive force, but as if an effective repulsive component exists on cosmic scales. A force at the edge of physics. These extreme aspects of gravity force scientists to ask new questions about the fundamental nature of reality. Black holes raise the information paradox. Gravitational waves reveal the dynamic structure of space-time, and dark matter and dark energy deepen the unknowns about the fate of the universe. Together, they point to the need for a new physics beyond the frameworks of Newton and Einstein. In the end, gravity is not just a force that provides order, it is also a puzzle that contains within itself the mysteries and contradictions of the universe. Understanding its extreme faces may open the door to one of the greatest revolutions in the history of physics. The theories of tomorrow: string theory, gravitons, and quantum gravity. Gravity is one of the four fundamental forces of nature. Yet it is the only one that has not been successfully unified with the other three: electromagnetism and the strong and weak nuclear forces. This mismatch underlies one of the greatest intellectual problems in physics. How can a single, unified theory reconcile general relativity with quantum mechanics? In classical physics, gravitation is described as the curvature of space-time. But on the subatomic scale, things change. Quantum physics describes a world where particles behave according to wave functions and uncertainty. In environments where both systems must operate simultaneously, for example, at the centers of black holes or in the first moments of the universe. Neither general relativity nor quantum mechanics alone is sufficient. This deadlock gives rise to the need for a new framework: quantum gravity. One of the leading approaches in this area is string theory. According to string theory, the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. Different modes of vibration correspond to different particles such as electrons, photons, or quarks. Interestingly, string theory naturally includes a hypothetical quantum particle called the graviton, thought to mediate the gravitational force. If this particle were ever observed experimentally, it would prove that gravity has a quantum nature. However, this has not yet happened. The graviton's interaction is so weak that detecting it is extremely difficult. Another approach is loop quantum gravity. This theory proposes that spacetime itself has an atomic, discrete structure composed of quantum loops at the Planck scale. This granular geometry may resolve the singularity problem at the beginning of the universe. Instead of collapsing to an infinitely small point, spacetime undergoes a kind of quantum bounce and begins to expand. The holographic principle has also opened a new path in quantum gravity research. It suggests that all physical information in the universe may be encoded on a lower dimensional boundary surface. Just as a three-dimensional hologram can arise from a two-dimensional surface, the apparent three-dimensional reality of the universe might be described on such a lower dimensional framework. This idea offers important clues for resolving the information paradox associated with black holes. All of these theories remain largely mathematical and theoretical. But experiments at particle accelerators like CERN, observations with space-based telescopes, and detailed studies of gravitational waves are opening ways to test these hypotheses. Physicists hope one day to achieve a final theory that unifies gravitational force and quantum mechanics under a single roof. Such a theory would allow us to understand not only the centers of black holes, but also the origin and ultimate fate of the universe, and perhaps even the possibility of multiple universes. The future of gravity research will not merely fill a gap in physics. It will also transform our understanding of the deepest nature of reality. Gravity. Beyond a simple act of falling, it is the invisible bond that weaves together and holds up the entire structure of the universe. From Aristotle's idea of natural place to Newton's apple, from Einstein's curved spacetime to our ongoing search for quantum gravity, this force has steered the course of humanity's intellectual history. Gravity does more than keep planets in their orbits. It bends the flow of time, guiding the birth of stars and the silent collapse of black holes. At the same time, it is indispensable for the balance of our bodies, the rhythm of our hearts, and the continuity of life. As science today strives to unravel gravity's behavior on the smallest scales, it also reminds us of a larger question. Understanding the universe involves not only calculations, but also grasping the deeper meaning of existence. And perhaps the greatest lesson of this invisible dance is this: we are small figures on a cosmic stage, moving to the rhythm of gravity. Yet precisely because of that, we are free enough to imagine the greatest secrets of the universe.